Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazim Abdul Halim. Metric number DD180079. Further on, I will tell you about my group member. For the first row, at the left side is Nur Aina Izzati binti Musa. In the middle is Izul Faris bin Abdul Aziz, and for the right side is Muhammad Hanif bin Sarwi. For the second row, at the left side is Izzatul Alia binti Mazlan, and then for the right side is me, Muhammad Hazim Abdul Halim. So before I continue to our main topic, I would like to tell you the difference between type of heat transfer, which is conduction, convection, and radiation. Okay, for the conduction, energy transfer by direct contact. Energy flow directly from warmer object to cooler object. They can occur within one object and continue until object temperature are equal. Next, for the convection, they occur in gases and liquid. The movement of the large number of particles is same direction, and then next occur due to different intensity. Lastly, cycle occur while temperature different exists. Okay, lastly, for our main topic is radiation. Radiation energy transferred by electromagnetic wave such as light, microwave, and infrared radiation. Next, all objects radiate energy and then can transfer energy through empty space. Lastly, I will tell you about radiation heat transfer. What is radiation heat transfer? Radiation is the transfer of heat by means of electromagnetic wave. In fact, the heat received on Earth from the Sun is the result of the electromagnetic wave traveling through the void of the space between the Sun and the Earth. All objects radiate energy in the form of electromagnetic wave. So that's all from me. Thank you.
Assalamualaikum and hi, my name is Izul Faris bin Abdul Aziz, and today I want to present about the theory of radiation. The theoretical foundation of radiation was established in 1864 by physicist James Clerk Maxwell, who postulated that accelerated charge or charging electric current give rise to electric and magnetic fields. These rapidly moving fields are called electromagnetic wave or electromagnetic radiation, and they represent the energy emitted by matter. In 1887, Heinrich Hertz experimentally demonstrated the existence of such wave. Electromagnetic wave transport energy just like other wave, and all electromagnetic wave travels at the speed of light in a vacuum, which is c equal 2.9979 times 10 power of 8 meter per second. Electromagnetic waves are characterized by their frequency or wavelength, where lambda equals c over v. The speed of propagation in a medium is related to the speed of light in a vacuum by c equals co over n, where n is the index of refraction of that medium. The commonly used unit of wavelength is the micrometer or micron, where 1 micrometer equal to 10 power of negative 6 meter. Unlike the wavelength and the speed of propagation, the frequency of an electromagnetic wave depends only on the source and is independent of the medium through which the wave travels. The frequency, the number of oscillations per second of an electromagnetic wave, can range from less than a million Hz to a septillion Hz or higher, depending on the source. The wavelength and the frequency of electromagnetic radiation is inversely proportional. It has proven useful to view electromagnetic radiation as the propagation of a collection of discrete packets of energy called photons or quanta, as proposed by Max Planck in 19,000 in conjunction with his quantum theory. In this view, each photon of frequency is considered to have an energy of E equal hv equal hc over lambda, where h 6.6256 times 10 power of negative 34 is Planck's constant. The energy of a photon is inversely proportional to its wavelength. Therefore, shorter wavelength radiation possesses larger photon energies. It is no wonder that we try to avoid very short wavelength radiation such as gamma rays and X-rays since they are highly destructive. Note that in the Einstein theory, h and c are constant, thus the energy of a photon is inversely proportional to its wavelength. Therefore, shorter wavelength radiation possesses more powerful photon energies, which is X-rays and gamma rays are highly destructive. Electromagnetic radiation covers a wide range of wavelengths from 10 power of negative 10 μm for cosmic rays to 10 power of 10 μm for electric power wave. As shown in the figure, thermal radiation wave is a narrow band on the electromagnetic wave spectrum. Thermal radiation emission is a direct result of vibrational and rotational motion of molecules, atoms, and electrons of a substance. Temperature is a measure of these activities. Thus, the rate of thermal radiation emission increases with increasing temperature. What we call light is the visible portion of the electromagnetic spectrum which lies within the thermal radiation band. Thermal radiation is a volumetric phenomenon. However, for opaque solids such as metal, radiation is considered to be a surface phenomenon since the radiation emitted by the anterior region never reached the surface. Note that the radiation characteristic of surface can be changed completely by applying thin layers of coating on them. A blackbody is defined as a perfect emitter and absorber of radiation. At a specified temperature and wavelength, no surface can emit more energy than a blackbody. A blackbody is a diffuse emitter, which means it emits radiation uniformly in all directions. Also, a blackbody absorbs all incident radiation regardless of wavelength and direction. The radiation energy emitted by a blackbody per unit time and per unit surface area can be determined from the Stephen Boltzmann Law. The figure shows the variation of blackbody emissive power with wavelength. Spectral blackbody emissive power is the amount of radiation energy emitted by a blackbody at an absolute temperature T per unit time, per unit surface area and per unit wavelength. The equation is called Planck Distribution Law and is valid for a surface in a vacuum or gas. For other mediums, it needs to be modified by replacing C1 by C1 over N2, where N is the index of refraction of the medium. The wavelength at which the peak emissive power occurs for a given temperature can be obtained from the Wien's displacement law. It can be shown that integration of the spectral blackbody emissive power EB lambda over the entire wavelength spectrum gives the total blackbody emissive power. The Stephen Boltzmann law gives the total radiation emitted by a blackbody at all wavelengths from 0 to infinity, but we are often interested in the amount of radiation emitted over some wavelength and band. To avoid numerical integration of the Planck's equation, a non-dimensional quantity f lambda is defined, which is called the blackbody radiation function. The function of f lambda represents the fraction of radiation emitted from a blackbody at temperature T in the wavelength band from 0 to lambda. The figure shows the fraction of radiation emitted in the wavelength between lambda 1 and lambda 2. So we move to radiation properties. A blackbody can serve as a convenient reference in describing the emission and absorption characteristic of real surface. Emissivity. The emissivity of a surface is defined as the ratio of the radiation emitted by the surface to the radiation emitted by a black body at the same temperature. Thus, the emissivity is 0 or lower and 1 or lower than 1. Emissivity is a measure of how closely a surface approximates a black body equal to 1. The total emissivity of a surface is the average emissivity of a surface over all direction and wavelength. Spectral emissivity is defined in a similar manner. Emissivity lambda T equal E lambda T divided by EB lambda T, where E lambda T is the spectral emissive power of the real surface. As shown, the radiation emission from a real surface differs from the Planck's distribution. The figure shows the comparison of the emissive power of a real surface and a black body. To make the radiation calculation easier, we define the following approximation. Diffuse surface is a surface which its properties are independent of direction. Gray surface is a surface which its properties are independent from wavelength. A gray surface should emit as much as radiation as the real surface as it represents at the same temperature. Equation shows the emissivity is a strong function of temperature. That's all from me. Thank you.
Assalamualaikum, my name is Muhammad Hanif and I will continue with the presentation. In radiation, there is absorptivity, reflectivity and transmissivity. Absorptivity is the fraction of irradiation absorbed by the surface, while reflectivity is the fraction of irradiation reflected by the surface. And for transmissivity is the fraction of irradiation transmitted through the surface. Applying the first law of thermodynamics, the sum of the absorbed, reflected and transmitted radiation must be equal to the incident radiation. For opaque surface, the above definitions are for total hemispherical properties. We can also define these properties in terms of their spherical counterparts. Absorptivity is almost independent of surface temperature, and it strongly depends on the temperature of the source at which the incident radiation is originating. In Kirchhoff's law, consider an isothermal cavity and the surface at the same temperature at the steady state equilibrium thermal condition. The total hemispherical emissivity of a surface at the temperature is equal to its total hemispherical absorptivity. For radiation coming from a black body at the same temperature, this is called Kirchhoff's law. And next, solar radiation. The solar energy reaching the edge of the Earth's atmosphere is called the solar constant. Owing to the ellipticity of the Earth's orbit, the actual solar constant changes throughout the year within plus minus 3.4%. This variation is relatively small, thus it is assumed to be constant. The effective surface temperature of the Sun can be estimated from the solar constant by treating the Sun as a black body. The solar radiation undergoes considerable attenuation as it passes through the atmosphere as a result of absorption and scattering. Absorption by the oxygen occurs in a narrow band about A equal to 0.6 micrometer. The ozone layer absorbs ultraviolet radiation at wavelength below 0.3 micrometer almost completely, and radiation in the range of 0.3 to 0.4 micrometer considerably. Absorption is the infrared region is dominated by the water vapor and carbon dioxide. Dust or pollutant particles also absorb radiation at various wavelengths. As a result, solar radiation reaching the Earth's surface is about on a clear day and much less on a cloudy day, in the wavelength band 0.3 to 2.5 micrometer. Scattering and reflection by air molecules and other particles are other mechanisms that attenuate the solar radiation. Oxygen and nitrogen molecules scatter radiation at short wavelengths corresponding to violet and blue colors. That is the reason why the sky seems blue. The gas molecules and the suspended particles in the atmosphere emit radiation as well as absorbing it. It is convenient to consider the atmosphere as a blackbody at some lower temperature. This frictious temperature is called the effective sky temperature. Using Kirchhoff's law, we can write alpha equal to epsilon since the temperature of the sky is on the order of the room temperature. The view factor of radiation. Radiation heat transfer between surface depends on the orientation of the surface relative to each other as well as the radiation properties and temperatures. View factors or shape factor is a purely geometrical parameter that accounts for the effects of orientation on radiation between surfaces. In view factor calculations, we assume uniform radiation in all directions throughout the surface. Surfaces are isothermal and diffuse. Also, the medium between two surfaces does not absorb, emit, or scatter radiation. There is three types of surface, which is plane surface, convex surface, and concave surface. Calculating view factors between surfaces are usually very complex and difficult to perform. View factor relation in radiation analysis of an enclosure consisting of surfaces requires the calculation view factors. However, all of these are not necessary. Once a sufficient number of view factors are available, the rest of them can be found using the following relations for view factors. That's all from me. Thank you.
Assalamualaikum. My name is Noraina Izzati binti Musa and my matrix number is AD170217. So here is the example for this topic, the radiation. So I'm going to read out the question first. This question is divided into two, which is A and B. The first one, A. Calculate the rate of heat transfer by radiation from a car radiator at 110 degrees Celsius into a 50 degrees Celsius environment if the radiator has an emissivity of 0.75 and a 1.2 meter square surface area. So we need to calculate the rate of heat transfer by radiation from a car radiator. The second one, B, is this a significant fraction of the heat transfer by an automobile engine? To answer this, assume the horsepower of 200, which is 1.5 kilowatt, and the efficiency of automobile engines as 25%. So we need to know whether it is significant or not. First, we are going to solve A first. So here we have T1, which is 110 degrees Celsius, and then T2 is 50 degrees Celsius. Emissivity is 0.75 and the surface area is 1.2 meters square. So we are going to calculate the rate of heat transfer by radiation. the formula that we are going to use is Q net over T equal to EA T2 power 4 minus T1 power 4. Oh, before I forget, the temperature we need to change it into Kelvin. So T1 plus 110 plus 273. So this one is 3 at 3 Kelvin, and then T2 is 323 Kelvin. So insert all of this into the equation. This is the Boltzmann constant. The value is always 5.67 times 10 to the power of -8. The emissivity is 0.75. Area 1.2. And the temperature T2 minus T1. T2 is 3 to 3 power 4 minus 3 at 3 power 4. Do the math and we get -543 watt. The value is negative because the temperature travels from hot to cold. Okay, this is the value for rate of heat transfer by radiation. So next we are going to answer the question B. Here we have, is this a significant fraction of the heat transfer by an automobile engine? So we have 200 horsepower or 1.5 kilowatt, and the efficiency is 25%. If we are talking about efficiency, it is always what is getting out over what we put in. So this is the efficiency. Doesn't matter whether it is energy or power, the concept will always be what is getting out over what we put in. So the out will be 1.5 kilowatt. We change it into watt, will be 1500, and then the in, going to calculate in. The efficiency is 25%, so 0.25, and we'll get 6000 watt. The question asks, is it a significant fraction? Is this a significant fraction? So compare this to negative 543 watt and 6000 watt. Surely this is not a significant fraction. The answer will be no, it is not. This is not a significant fraction.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Izzatul Alia binti Mazlan. Nombor matrik saya DD180031. Saya akan present tentang soalan kedua. So untuk soalan 2 ni, gambar ni menunjukkan a furnace of a cylindrical shape yang mempunyai radius sebanyak 2 meter dan ketinggian pun sebanyak 2 meter. Okay, base, top dengan side furnace ni semuanya hitam dan it's maintained at uniform temperature pada 500 Kelvin, 700 Kelvin dengan 1200 Kelvin. So dalam question ini, apa yang kita perlu cari ialah the net rate of radiation heat transfer to or from the top surface during the operation. So solution untuk soalan tadi, first kali kita kena tahu assumption yang perlu kita buat untuk soalan ni. Pertama sekali kita akan assume steady operation condition berlaku. Lepas tu the surfaces tadi macam kita tahu dalam soalan tadi semuanya hitam. Kemudian convection heat transfer dalam soalan tadi ialah tidak di-consider. Okay, so untuk formula dia kita pakai Q dot sama dengan A1 F12 sigma dalam kurungan T1 kuasa 4 tolak T2 kuasa 4 campur dengan A1 F13 sigma T1 4 tolak T3 4. Pertama sekali kita akan cari nilai area silinder menggunakan formula pi r squared. R kita masukkan, R radius kita tadi iaitu 2 meter dan kita dapat jumlah area dia ialah 12.57 meter squared. Seterusnya kita akan cari view factor from the base to the top surface of the cylinder iaitu F12 sama dengan 0.38. Untuk the view factor from the base to the side surface kita akan cari menggunakan summation rule. So formula untuk summation rule ialah F12 campur F11 campur F13 sama dengan 1. So manakala dalam formula ni ada F12, F13, kita buat gunakan ini F13 tolak F13 sama dengan 1 tolak F12 iaitu F13 kita dapat 0.62. Kemudian setelah kita dapat nilai F12, F13 kita akan masuk kembali ke dalam formula Q dot tadi di mana kita punya sigma ialah 5.67 kali 10 kuasa negatif 8. So kita masukkan nilai A1, F12, sigma, T1 yang kita dapat daripada formula T1 yang kita dapat daripada soalan, T2 dapat dari soalan, T3 pun kita ada daripada soalan. Masukkan dalam formula Q dot dan kita akan dapat nilai akhirnya iaitu negatif 7.62 kali 10 kuasa 5 watt. Okay. Negatif sign ni dia menunjukkan bahawa heat transfer tu berlaku pada top surface silinder ni. Okay, itu saja. Terima kasih.